Welcome again to the course Analysis of Several Variables, and we continue with the module 4, which is partial derivative and directional derivatives. And today we are going to discuss about the section 4.2, which is Jacobian matrix. So first we will define the Jacobian matrix. Let omega be open in Rn and A is a point in the omega. We define a function f from omega to Rm. So the function is basically from Rn to Rm in such a way that it has x is from x1, x2, xn, because we have here from Rn, and the function fx is equal, have a component up to m because it is on Rm. So therefore we got the such functions with the partial differentiable at the point A. So this function f should be partially differentiable at the point A. Means all the first order partial derivative should exist. So since we have here n variable, x1, x2, xn, n variable, so we should have n partial derivative for the function f. If such condition satisfied, then we can define a matrix involving all these partial derivative, and we denote this is as JFA. So JFA here, the J is for Jacobian, F is for the functions, and at the point A. And this matrix will be given as like this. JFA will be, now just observe it, that what you have in the first row, all the cases the function is f1. So it will be the derivative of the function component f1, okay, with respect to all the component. Then second row is for f2, and the last one will be fm, and partial derivative with respect to all the variables. So what we are getting here, you will see the number of the rows will be f1, f2, fm. So that is m number of rows. And how many columns? Columns is here x1, x2, xn. So therefore n column. So you are getting a matrix of f m by n. And this matrix is known as Jacobian matrix of f at the point A. So now we have a notes here that if f is from Rn to Rn, then the Jacobian matrix will be in the class of functions, a class of matrix m by n. Okay? So if you have f is from R3 to R2, then in this case JFA will be M2 by 3, means it will be 2 by 3 matrix. Okay, now let's have one example here. Here is that find JF1 minus 1 from FR2 to R3 defined by this f of xy equal ln 1 plus x square y square tan inverse xy and x plus y square. So we need to find the Jacobian at the point 1 and minus 1. So to do that, we will divide these functions in a component wise as per our requirement. So let's say a solution. So denote f1 xy is equal ln 1 plus x square plus y square. f2xy is equal tan inverse xy, and f3xy is equal x plus y square. Now we will calculate the partial derivative of each component at the point jf1 at the point 1 and minus 1, and with respect to both x and y. So del f1 del x at the point 1 minus 1. So this is equal del x. So since we are doing partial derivative with respect to x, so we will take the point 1 as x and fix y by minus 1 at the point x. This is equal del x of ln 2 plus x square at the point x is equal 1. So the derivative of this one will be 2x over 2 plus x square at the point x is equal 1. So this will be 2 over 3. So we got our first entry of the matrix is 2 by 3. So next we'll continue in the same way. So del f1 del y at the point 1 minus 1. So this is equal del y, and then we will have ln. So x is equal 1, we will put it. So 1 plus 2 plus 2 plus y square, and at the point y is equal minus 1. So this is equal 2y over 2 plus y square, so which is minus 2 over. So our next entry is minus 2 over 3. So in the next step, we are going to take the derivative of y2. So del f2 del x at the point 1 minus 1. So this is equal del x of tan inverse. So we put y equal minus 1. So this is tan inverse minus x at the point x is equal 1. So this is equal minus 1 over 1 plus x square at the point x is equal 1. So this is because d dx of tan inverse ax is equal 1 over a over 1 plus a square x square. So this will gives us minus 1 over 2. This is another entry of the matrix. Our next is similarly del f2 del y at 1 minus 1. So this is equal del y of tan inverse y at y equal minus 1. So this is equal 1 over 1 plus y square. So this is equal 1 over 2. And this will be 1 over. Next, we will have del f del 3, which is very easy. del f3 del x at the point 1 minus 1. So this is equal del x of, so our functions was here x plus y square. So this is x plus y square. So the y we can put it as 1. So x plus y at the point x is equal 1. So which is equal 1. So this is the entry of the matrix. The last one is del f3 del y at 1 minus 1. So this is equal del y, and x is 1, y square at the point y is equal minus 1. So this is equal 2y at the point y equal minus 1. So this is equal minus 2. This is another. So therefore, finally we have JF at the point 1 minus 1. So this is equal. I'll write the matrix and then we'll see that how it is coming. So it will be del F1, del X, del F1, del Y, and of course at the point 1 minus 1, then del F2, del X at 1 minus 1, del F2, del Y at 1 minus 1, del F3, del X at 1 minus 1, and del F3, del Y at 1 minus 1. So we got all those values and we need to just write it here. So we'll go back and check what are the values. So we got 2 over 3 minus 2 over 3 minus half half. 2 over 3 minus 2 over 3 minus half half, and here we have 1 and minus 2. So note it here, f was from R2 to R3. So the expected matrix JF 1 minus 1 should be M from M in the class M3 by 2. So this matrix is 3 rows, 2 columns. So that's all. So now we have a theorem here. This theorem says that let omega be open in Rn and A belongs to omega. Then the functions f from omega to Rm is differentiable at A. This is given. The function is differentiable at the point A. So now let lambda belongs to R. Then we have f dash A. Okay, so derivative of this function, since it is differentiable, so derivative of this functions will be linear from Rn to Rm, and the matrix of f dash A is equal Jacobian of the functions at A. So the derivative functions, if you convert it to the matrix form, then it will be same as the Jacobian of the function f. Next is that this can be written as the functions f dash A operating on H belongs to Rn, is equal JFA dot H. So it will be, can be, means take the matrix and take the product of the matrix with the matrix H. then you will get same as the dot product of the functions. So this is the properties of Jacobian matrix, or this is the relations between the Jacobian matrix and the derivative of the function. We have another theorem, and this theorem says that let omega be open in Rn, then and A belongs to omega, the point. Then the function f and g both are from omega to Rm, differentiable at A, same is the same point. Then the Jacobian of that linear combinations of those functions f and lambda g is equal the Jacobian of f at the point A plus lambda Jacobian of g at the point A. Okay, so this can be proved by using the concept, basic concept of the differentiability. Now, next theorem is that if omega be open in Rn and A is a point in the omega, and let small omega be open in Rm, then the functions f from capital omega to small omega is differentiable at A, g is differentiable at f of A. So these are given conditions. Okay, so function f is from capital omega to small omega, g is from small omega to the set R is differentiable at f A. Then the Jacobian of the composition functions g composition f at the point A is equal Jacobian of g at the point fa multiply Jacobian of f at the point A. So you have to understand here the Jacobian g will be defined on fa. So if we draw a Venn diagram, so that's you have here the omega which is on Rn, then here you will go, it will be on Rm, there is a set small omega, and then from omega to Rs. So we have a function here, this f, and this is g. So therefore, if the point A is here, so this is the point A, then there will be a point f of A. So this function is going there. So this is by f, and from f A we have here this. So this is g. So this is g of f. So therefore Jacobian of this function, so it for the g, Jacobian for g will be defined in the point f A. Now we have an examples where we have to find the derivative of the composition, Jacobian of the composition function. So we have given function f is from R2 to R3, and this is defined like this: e to the power xy first component, x square y second, and x plus 2y third component. And g is from R3 to R2 defined by this cosine pi x and x e to the power y g. Then we have to calculate the Jacobian of the composition of these two functions at the point 1 and 0. Okay, so we recall from the previous theorem that Jacobian of this composition is Jacobian of Fa and then multiply with Jacobian of F at the point A. So first we calculate this Jacobian of F at the point 1, 0, and then we'll calculate Jacobian of G at the point F 1, 0. So given that F R2 to R3 is defined like this, so we take the component of this function. F1 is e to the power xy, F2 is x square y, and F3 is x plus 2y. Then we calculate the partial derivative of each component with respect to x and y. So F1 xy at the point 1, 0. So again, by adopting the same method, we put y equals 0 and keep x as a variable. And then we are getting this one e to the power x0, which will be 1. So therefore, partial derivative of 1 will be 0. So we got one entry is 0. We continue with this with respect to y and the component f1. And in this case, we will keep x is the constant value and y is the variable, and then we got the derivative, and at the point y equals 0 the value is 1. So in this case matrix entry is 1. We continue on f2. So f2 1 0, so y equals 0, so it will become 0, the derivative is 0. Same way f2 with respect to y, and then we put x equal 1 and x equal 1 here and y as it is. So at the point y equals 0, so the partial derivative is 1. So at the value y equals 0, the derivative is also 1. And our last one is easy, f3x at 1 0 is equal derivative of x, which is 1. And then f3y, that's also 1 plus 2y, because we put here x is equal 1, y as it is. So therefore we take the partial derivative, and the derivative is 2 at the point 0, so the value is 2. So we got the matrix form for Jacobian matrix for the function f, which will be 0 1 0 1 and 1 2. It's clear. Again, check it. We have f is from R2 to R3. So the Jacobian f at any point 1 0, it will be 3 by 2. So our matrix here 3 by 2. So it's correct. Now we'll calculate the for the functions R3. G is from R3 to R2, and it's defined by this function. So again, we'll consider two component of G. G1 is xyz equal cosine pi x, and G2 is x e to the power y and z. Then we also note that f10, because we have to calculate at G f10. So therefore, we need to know what is the value of f10. So f10 from the previous functions, it will be 1 0 1. So we have to calculate the Jacobian for G at the point 1 0 1. So again, we continue with the similar partial derivative, and so del G1 del x at f10. So this is the point, and it is the partial derivative of cosine pi x. So this one, and this will be minus pi sine pi x at x equal 1. So it will become sine pi, and sine pi will be 0. Then the second one is with respect to y. So when we take with respect to y, we have to put x is equal 1 here. So x is equal 1, y is as a variable, and g is equal 1. So there is no g in this case, no y. So therefore it will become cosine pi, and which is a constant with respect to y, so the derivative will be 0. Then here we have to do with respect to g also, and again like the y we have here, the derivative is equal 0. Now we'll calculate for G2. So G2 101 with respect to x. So if you keep x as the variable, so from here x is the variable, y is 0, z is equal 1. So it will become x e to the power 0 1, so which is nothing but the partial derivative with respect to x at x is equal 1. So this is equal. Next we will take with respect to y. Then again from this part we have x is 1, y as it is, and this is 1. So derivative of with respect to e to the power y, so y equals 0, and then it will become e to the power 0 is equal 1. And the last one is with respect to g, again with the repeating process, you will get del z derivative, and this is only g is equal 1. This is g is equal 1, and then you will get it, the derivative is equal 1. So we got now the matrix for Jacobian of G. So this is equal, we got this matrix, and the matrix is 0 0 0 1 1 1. Again we recall G is from R3 to R2. So the matrix Jacobian G, whatever the point it is, in this case F10, this will be 2 by next we'll have the finally we have the answer here. So Jacobian of G composition F at the point 1 0, not F10, at the point 1 0, which will be the Jacobian of G at the point F10 and Jacobian of F at the point 1 0, and then we got the matrix. So this is, we got this matrix 2 by 3, this is 2 by 3, and this is 3 by 2. So product is well defined, and if we take the product we will get 2 by 2 matrix 0 0 1, and this is the Jacobian of G composition F at the point 1. So now we have a definitions here. It is function of type C1. Okay, in this definition, so let omega be open in Rn, and we have a function f, we denote it as C1 omega, which means that f is a C1 type function if f is partial differentiable at all points on omega. So that means any first order derivative with respect to all the derivative, or with respect to all the variables that exist at any point. And this all the first order partial derivative, which we denote as del f del xi, and I is 1 to n, are continuous on omega. So two condition is there, which it should be differentiable at all point in the on omega, and should the all the partial derivatives should be continuous. Then we call that function as a type C1. Now we have a theorem is that it gives a relation between the functions f c1 omega. Yes, type c1 function is how it's related with the derivative. So it says that if f is on c1 omega, then it is differentiable on omega. And from a previous theorem we have that if it is differentiable, then we can always like this. Okay, so which will be can be later, means we can say that from the previous one theorem. So this is Jacobian of f at the point A, okay, dot h. Okay, now we have a problem here that prove that f R3 to R defined by f x y z is equal 1 over square root of 1 plus 4x square plus y square plus z square is differentiable on R3, and we have to find the derivative of this function. So this means that if we are able to show that this function is a C1 type, then it is enough to conclude from the previous theorem that it is a differentiable function, and we can calculate the derivative. So first we'll show it, calculate the partial derivative of this function. So del f del x. So this is equal del x of 1 plus 4x square plus y square plus z square to the power minus half. So by the rules of the partial derivative, we'll get it here. This is equal minus half 1 plus 4x square plus y square plus z square minus 3 over 2, and the derivative of 4x square will be, so partial derivative of 4x square, so which is 8x. So we can simplify it, 1 over 2 1 plus 4x square plus y square plus z square to the power 3 over 2, and this will be 8x. So this will be minus 4x over 1 plus 4x square plus y square plus z square to the power 3 over 2. And we can see that this is a continuous function. Okay, because on R3, so this function is always defined because already square root of 1 plus 4x square plus y square z square is defined. So denominator never be 0, and numerator we have only 4x, which is a polynomial kind of the thing. So it's a rational functions where the denominator never be 0. So it's continuous. So in similar way, we'll calculate similarly del f del y. So this will be minus y squared. So derivative of y squared is 2y. So it will be, we can write it directly. So the first part will be same. So this is 1 over 2, 1 plus 4x squared plus y squared plus z squared, and then we will have a partial derivative of y squared. So this is equal minus y over, so this is 3 over, minus y over 1 plus 4x square plus y square z square over 3 over 2, which is again a continuous function. So then we have here last one, del f del g. So this is equal minus 1 over 2 1 plus 4x square y square z square to the power 3 over 2, and then derivative 2z. So this is equal minus z over 1 plus 4x square y square z square to the power 3 over, again it is continuous. So therefore del f del x del f del y del f del z exist on R3 and all of them are continuous. So therefore, by the theorem here, that if f belongs to C1, then it will be differentiable, and the differentiability can be calculated by this formula. So therefore, we get it here. So therefore, f is belongs to C1 R3, and by theorem, previous slide, we have f is differentiable on omega, and if dash, now for h1 h2 h3 belongs to R3, f dash x h, so this is equal h, f dash x h is equal h1 del f del x, here is x y g, plus h2 del f del y plus h3 del f del z. So this is equal, we'll have here already calculate. So this is equal minus 4x. So we'll write it together. So this will be minus 1 over 1 plus 4x square plus y square plus z square to the power 3 over 2, and then you will get it here 4x h1 plus y h2 plus z h3. So this is the answer. Okay, so we complete section 4.2, and then next lecture we will have directional derivative, which is 4.3, and the gradient of functions, which is 4.4. And then we'll have some numerical example.